The production of this program is made possible thanks to the support of the following and viewers like you. Captain James T. Kirk starts each episode of Star Trek saying, "Space, the final frontier." These are the voyages of the Starship Enterprise. Its 5-year mission? To explore new worlds, to seek out new life and civilizations, to boldly go where no one has gone before. Well, 5 years is a long time, and packing 5 years of food would be impossible. While the writers of the series dealt with the production of food in a variety of ways, everything from colored cubes to a protein resequencer that could replicate certain foods, and an onboard hydroponic greenhouse to grow fruits and vegetables, the reality of producing food in space is extremely complex. And if we are planning 3 or more year missions in space, we need to learn how to grow food on the way and once on the planet that we land on. At the University of Guelph, Professor Mike Dixon and a team of researchers has been tackling this challenge for 20 plus years. And Dixon says we can grow food, not all the food we grow here on Earth, but we can grow food. That, however, is just the beginning. Being in space means you have no choice. You have to have a zero environmental footprint. That means zero waste. The waste you produce has to be recycled and put back to work immediately. Dixon adds, we can't wait for nature because nature isn't fast enough. I invited Dr. Michael Dixon to join me for a conversation that matters about growing food in space and what lessons we can apply to growing climate-smart food here. Mike, welcome.
My pleasure, Stuart.
What is it that you're doing in your lab as far as the production of food that we should really care about?
We're trying to come up, and we've been at this for a while, over 30 years now, looking at how controlled environment agriculture, how to grow food in harsh environments. And we're using outer space as the technical pull. So if we can solve food production requirements in outer space, the moon and Mars in particular, then the technical challenge of, say, Canada's north or deserts of the Middle East become almost child's play.
Yeah, except for it's not. How complicated is it to be able to determine how to grow food in space? What are the elements that are in motion?
Well, you need to have really very tight control over light intensity, light quality, CO2, temperature, humidity, nutrients, and water, and in the case of space exploration, pressure. So we have very unique controlled environment chambers here that can deal with all of that and simultaneously monitor a plant's physiological response to whatever environment cocktail you throw at it in terms of photosynthetic gas exchange, CO2, oxygen, and water vapor. So we follow second by second how the plant is dealing with each of those responses to the environment and use that to optimize then the environment control recipe for whatever application, especially only in a controlled environment application.
So when you think about how complex the Earth's environment is, how is it that you're able to duplicate that?
Well, we don't want to duplicate it. Plants have the capability to respond to a huge range of almost every environment variable except temperature, and it's almost half an order of magnitude there. So plants do very well. They'll acclimate to almost anything. We've learned that you can take the pressure down to 1/10 of Earth's atmosphere, which is remarkable. You and I can't handle that, but plants, as long as you give them enough oxygen for respiration, a little squirt of CO2 and some water vapor so that they don't dry out, grow like they're in your backyard at 1/10 of Earth's atmospheric pressure.
Do you need nitrogen as well?
We use nitrogen as a buffer gas, but basically 7 kilopascals of oxygen, 0.1 kilopascals of CO2, and 1.2 or 3 kilopascals of water vapor, and then the rest up to about 10 kilopascals of nitrogen or any other buffer gas, argon, whatever. But oxygen, CO2, and water vapor is the recipe for plants. They can adapt to or acclimate to virtually anything we throw at them. So they're not the limitation in designing the conditions and the hab for space exploration for the moon and Mars. It's us. We're the main limitation. We need, we're kind of handy. We're kind of stuck on 21 kilopascals or 21% oxygen. And so that will be the main limitation. So we'll design since we know that the gloves are off basically as far as plants are concerned, it turns out that pollinators, for example, we put bees in our chamber, tried to figure out how you could mess with the atmosphere composition and pressure and still having pollinators doing their job for example, tomatoes, which we don't have self-pollinating tomatoes yet. So turns out that pollinators, once you get down to about a third of Earth's atmospheric pressure, remember plants can handle a tenth, so once you get down to about a third, well, bees can't fly. The physics of flight are defeated by that. Plus, they're kind of not happy about the low oxygen either. So we kept the pressure down and increased the oxygen so we wouldn't wipe out our little pet bee hive colony. And turns out they came back to life happily, and they walked to work because they couldn't fly.
Now, I got to get you to hang on for a second while we take a quick commercial break. The production of this program is made possible thanks to the support of the following and viewers like you. So you're going to send bees to space as well?
Well, bees are probably not the best candidate for pollinator. There's lots of others. But we'll definitely be looking at how do all the different organisms, including us, deal with the really strange environment conditions, because we're not necessarily, in fact, we're almost certainly not going to have full Earth atmosphere with the pressure and the atmosphere composition that we're used to and know and love, because it's too expensive. The mass and energy cost of containing that is almost prohibitive. So when we go to Mars in particular, the atmosphere composition and the life support machine, the plants that we take with us, will deal with a different environment than what we have here on Earth. So we need to figure out what are the limits, where are the thresholds of atmosphere composition and pressure that, because we'd like to have a low mass inflatable system like Matt Damon had on Mars in The Martian. If you haven't seen that, I advise it. It's one of the more scientifically accurate stories in recent times, except for the wind. The atmospheric pressure on Mars is less than 1% of Earth. So for it to mess my hair, it'd have to be some pretty serious wind. Nevertheless, the arithmetic that Matt Damon was doing with his potatoes, it's exactly what we do here. We try and figure out what the nutritional composition of the plants are that will sustain human life indefinitely. And of course, you want more than potatoes. You want, a good vegetarian diet, unfortunately, but you want a range of commodities that give you a nutritional, balanced diet that is also psychologically appealing. You don't want to miss out on the hort therapy aspects of long-term space exploration. So those are the limits within which our program operates.
Okay. And so we can grow leafy greens. Can we grow tomatoes?
Absolutely. Oh yeah. I mean, the controlled environment agriculture sector, especially here in Canada, where we have this harsh environment, snowbank in Canada is a tough place to grow a plant. So the greenhouse industry has been, very successful over the decades, especially the last 50 years. So growing the three big ones, which are peppers, tomatoes, and cucumbers. Those are the three main commodities that come out of controlled environments. And the new vertical farming subsector of agriculture is stuck on leafy greens because they are the easiest, they're the quickest, to turn around, and they address a certain specific market sector that will handle that. But there's going to have to be some changes. I mean, lettuce is not food, to me at least, until you put the ranch dressing on it. So we need proteins and carbohydrates. So we need to expand the scope of commodities that we produce in vertical farms.
And so can we grow carbohydrates in space?
Yes, we can grow anything. We have the technology today, literally. We simply don't have the political or economic will to do it.
It's money.
It's money, obviously. It's always money. And you know, the space exploration is not a cheap venture. But what most people don't really seem to get is that you spend the money in the Canadian economy. The currency of space travel is mass and energy. And you want to mitigate those two as much as you can. And the technologies required to achieve that are what we're developing here. That's you know, you want to drive the mass of the food production system down. You want to drive the energy requirements of the food production system down, and everything else in space exploration.
Can you grow lentils and nuts in space?
Yes, yes. There's no limit to, I mean, with the high fidelity environment control that we can exploit from research like this, it comes down to the political and economic constraints of integrating that kind of technical challenge into what we currently call human space exploration.
The benefits of developing this technology are, one, yes, you're growing food in space, but then I think you possibly have a much more valuable export or spin-off product. And that's the technology and the equipment that goes with this.
Exactly. I mean, food determines how far from Earth we can go and how long we can stay. Plain and simple. I don't often get a mission to go to the moon or Mars to grow food. So no mission, no money. So indeed, this entire program, multi-million-dollar research agenda here with some of the most sophisticated controlled environment infrastructure in the world, is devoted to pursuing that objective of growing food on the moon and Mars in those harsh environments, but spinning that technology solution into, for example, you can't throw anything away when you go to space. So we have to learn how to recycle everything. We're really bad at it at the moment. We're getting better, but...
Who? We collectively on Earth, or you in space?
Us Earthlings are not very good at recycling stuff. You can't throw stuff away when you go to space. Now, we do throw a lot of stuff away on the International Space Station because we don't have the technology to recycle it adequately, and the size of the space station limits the scope of what you can do with stuff that you accumulate and try to recycle. So we put it in a box and send it home, or we put it in a box and burn it up on reentry. You've heard Chris Hadfield talk about shitsicles. Nevertheless, some of those shooting stars that you see are buckets of human waste coming from the space station. You heard it here first. But you know, the space exploration is a profoundly powerful economic engine, especially for a country like Canada, and especially in this particular field of biological life support, food, plants in space. It determines how far we can go and how long we can stay. So we'll definitely do it, and we'll find life on Mars, or at least the vestiges of some sort of microbial life. I'm absolutely certain of that. You heard it here first, Stuart. So that technical challenge of going to a place like Mars, not throwing anything away, and growing enough food to support, say, a crew of 8 indefinitely, that's the Holy Grail. And we won't get there quickly. We'll incrementally advance the technology of food production to the point where it offsets resupply from Earth and limits the cost, then the mass and energy cost of life support.
This is our second break. We'll be back in a moment. The production of this program is made possible thanks to the support of the following and viewers like you. So if we can learn how to contain the environment, in essence, you have a zero emissions footprint or net zero because you've got a biogas loop, right?
Right.
What do we learn from being able to do that in space that we can apply here on Earth?
Just the recycling technology, the sensors to recycle. We can't recycle water in a greenhouse today very efficiently or very effectively. Basically, we have two sensors, pH and electrical conductivity. And they are relatively indiscriminate sensors on the quality of the nutrient solution, the hydroponic system that you're attempting to recycle indefinitely. And you have to do it in space. I don't have an option. I must, because the way we handle it here now is when the nutrient cocktail that's in the hydroponic solution gets a little out of whack, we throw it away and start again. That's our solution here on Earth in our agriculture sector.
So if you can figure out how to do that in space, why can that technology not be applied here on Earth?
It will absolutely be applied here on Earth long before it's deployed in space. If we can develop reliable, robust sensors that can meet the challenge, the technical challenge of reliably monitoring nutrient management solutions in a hydroponic system, that is the biggest technical black hole in controlled environment agriculture today. We have, all the other environment variables, light and CO2 and temperature and humidity and irrigation, but nutrients, can't figure that one out yet. It's really hard to do. We've been trying for decades now, not alone. There's lots of people around the world who are putting some energy into this effort because it is significantly important, and we're not there yet. And I have we don't have that Star Trek tricorder to tell you what the content and how to maintain feedback control over the nutrient solution loop. We've got to get there.
So one of the big concerns that people who are outside of the agricultural space have about agriculture is its CO2 and nitrogen emissions. They have this idea, or we want to embrace this idea, that somehow we can reduce that environmental footprint by reducing the use of artificial fertilizers and removing motorized vehicles that are roaming around in fields burning diesel fuel.
Yeah, and okay, the vertical farming sector is addressing a piece of that by trying to put food production, or so-called food production, into as local an area as possible to mitigate, trying to ship lettuce from Salinas, California to Toronto. It seems a bit silly, but that's what we do. So addressing that and modifying the distribution networks of a lot of food products is being addressed by that controlled environment approach. But there's so many, just think of all the commodities that you have to move. Wheat and soybeans and corn and the list is rice. The list is kind of daunting in terms of trying to fix it for everything. So you have to pull back and look at the system from a distance, and then get up close on making incremental advancements on various elements. Just pick away at it, because we have the technology in many respects. We're going to get there with the nutrient systems. We're getting there rapidly with LED lighting, which has transformed the neighborhood really of controlled environment agriculture, because now that's what allows you to stack them up 15 levels high. You can put these low heat emanating LEDs and high efficiency LEDs that are getting better and better every day and cheaper. So that's a good thing, and it will continue to improve, and it expands the scope of the technical solutions that we can bring to bear on high density food production.
One other way in which we can reduce environmental footprints, especially for the food that we grow in Canada, is based on the work that you're doing. Are you going to be sharing the science or technology that will help to increase yield? And I ask that because if a farmer can get a greater yield out of that acre of land, will the ultimate environmental footprint actually come down for food production?
Yes, yield is the ultimate metric for the farmer. The yield determines his return on his investment for infrastructure and everything. We're looking at coming up with that environment control recipe. And among the variables that we measure are the yield and the quality. Because one of the major things that's confounding the vertical farming sector is the quality of the product that they produce, because you can have the same genetics, but if you mess around with the environment, just the color of the light even, you can generate completely different outcomes in terms of the quality of the product. We've grown products here and changed the size, shape, color, taste of different food commodities just by messing with the color of light. So we're using high fidelity controlled environment to zero in on the recipe that achieves not only optimal yield, but optimal quality. Things like shelf life are profoundly important in strawberries, for example. So struggling with the environment control recipe that yields a good tasting strawberry that has the robust shelf life to withstand whatever treatments post-harvest brings to it. Those are among the incremental advancements that we'll be making.
Third and final break. We'll be right back. The production of this program is made possible thanks to the support of the following and viewers like you. When you're talking about yield, you also talked about the genetics. And I can't help but think of the work of Norman Borlaug when he was using gene splicing, blending strains of wheat together and wound up creating an abundant crop of maize in Mexico. And ultimately, India picked up that, and they went from starving nations to both being abundant producers. How important is the genetic role as far as you're concerned in working with plants so that they can be their best in the space environment?
Right. Well, certainly the breeding, the genetics, even the modified genetics, if you must, is half the story. Plants are a product of their environment within the limits of their genetic complement. And so the genetics are profoundly important to help you determine the threshold of environment variables that you can play with to come up with optimal yield and optimal quality. But my biased opinion, of course, being a controlled environment type, is that okay, Mr. Breeder, give me your best, and I can turn it on its ear just by messing with the color of the light. So there's a lot of work to be done, a lot of fundamental basic research on plant-environment interaction, and you need this kind of technology to do it. So this isn't, the stuff that I've showed you out here in the lab is not commercially viable as technology, but the recipes that come away from investigating the photosynthetic gas exchange of a specific plant under certain environment control conditions, that high fidelity recipe is how we will advance the technology and transfer that. So I give that recipe to the greenhouse grower even, or especially the vertical farmer.
So to conclude, are you hopeful that we'll be able to produce the quantity of food that's required and improve our relationship with the environment in which we grow it?
That's certainly possible, yeah. Exploiting technical solutions to recycle more efficiently and more effectively, maintain environmental standards, if you will. I'm not sure that it certainly isn't going to happen immediately, but as long as everyone keeps their sense of humor and and moves along with incremental advancements and just keep piling it on rather than trying to reinvent stuff every 17 years. There seems to be a cycle in the scientific community. Every 17 years, you have to rediscover everything with slightly more modern technology. Let's keep it written down.
I like what you say about incremental improvements, but it flies in the face of those people who like to say, no, if you can imagine it, you can achieve it by 2030.
Yeah, nice. Well, I've been talking about this stuff for 30 years now, and it's always mañana, but we definitely have made some major modifications and improvements to controlled environment agriculture technology in the last 30 years. It's, the stuff that we conceived of in greenhouse technology 30 years ago, we've gone so far beyond what we can do now with breeding and tissue culture, with environment control, really top quality hardware that is becoming more and more economical. So it is realistic to apply the kinds of high fidelity environment control technologies we deploy here at a commercial scale.
Thank you, Mike. Always a pleasure to see you.
Pleasure, Stuart, as always.